Have you ever really thought about what happens when you click Join Meeting? 1 second you're at your desk, and the next you're on screens all over the city, maybe even all over the world. It feels so simple, right? But behind that one click is a mind-boggling feat of engineering. So today, we're going to pull back the curtain and see the hidden architecture that makes millions of Zoom calls possible every single day.
So check out this number, 300 million. Back in early 2020, when the world basically went remote overnight, Zoom's daily meeting participants exploded from about 10 million to this number in just 3 months. That is a 30 times increase in traffic, almost literally overnight.
So that's a big question, right? How on earth did they build a system that could not only work in real time, but also handle that kind of insane, unprecedented growth without just collapsing? Well, the answer is all in some really brilliant system design.
See, the whole game with real-time video is delay, or what engineers call latency. For a conversation to feel even remotely natural, the delay between you speaking and someone else hearing you has to be under 150 milliseconds. That's literally faster than the blink of an eye. Any longer than that, and things get awkward, you start talking over each other, it just breaks. This is way harder than streaming a movie, because a movie can load a bunch of data in advance, it can buffer. A live call? Nope. There is zero room for delay.
So to solve this massive challenge, Zoom doesn't just treat every call the same way. The system is actually really smart. The first thing it does is look at how many people are in the meeting, and then it picks one of two totally different paths for your data to travel down. So these are the two main blueprints. If it's just a simple one-on-one call, Zoom will often use what's called a peer-to-peer connection, or P2P. That just means your computer sends your video directly to the other person's computer. It's the shortest, fastest route. But the moment you add a third person, that whole system falls apart. For larger meetings, everyone connects to a powerful central Zoom server, which acts like a traffic controller for the entire call.
All right, so let's follow the journey of your voice and video. We'll call it a data packet. Before this tiny packet even leaves your computer to go out onto the wild internet, a few really crucial things have to happen first, right there on your own device.
And the magic really starts with a technology called WebRTC. The best way to think of WebRTC is like the travel agent for your data. It's a set of tools that's already built into your web browser, and its job is to get your audio and video all packed up and ready for its big trip across the world.
And WebRTC does three main things. First, it captures the raw information from your camera and your microphone. Second, and this is maybe the most important step, it compresses that data. See, raw video is absolutely huge, so it uses something called a codec to shrink it way, way down. And finally, it packages all that compressed data up, ready to be shipped out.
Now, here is a big part of Zoom's secret sauce. Their codecs are incredibly smart. They do this thing called adaptive bitrate streaming. What that means is, if your internet connection is a little slow, the codec automatically lowers the video quality just enough to keep the call from freezing. But if you've got a great connection, it'll send you that beautiful, crisp HD video. It's constantly adjusting in real time for every single person on the call.
Okay, so our little data packet is compressed, packaged, and it's ready for an adventure. Now it has to fly across the giant, chaotic superhighway that is the internet. So how does Zoom make sure it gets there fast and in one piece? Well, it has to pick the right vehicle. So instead of using a protocol like TCP, which is like a guaranteed postal service that makes sure every single piece of your email arrives perfectly, Zoom uses UDP. You can think of UDP as being more like a live radio broadcast. If you miss one word because of static, the host doesn't stop the show, right? They just keep going. For video, it's way better to miss a single pixel than to have the entire call freeze up waiting for that one missing piece. It's all about speed over perfection. And to guide that speedy little packet, Zoom has this enormous global network of its own data centers. So when you join a meeting, it doesn't just send your data randomly. It instantly connects you to the server that is physically closest to you. It's basically a GPS for your data, always finding the shortest, quickest route to keep that delay, that latency, as low as humanly possible.
Okay, but remember how we said large meetings take a different path? For any call with more than 2 people, our data packet has to make one very, very important stop before it reaches everybody else. You can think of this stop as the call's grand central station. This central hub is a special high-powered media server called a selective forwarding unit, or an SFU. And honestly, this piece of technology is the real key to making huge meetings work at all. Instead of your little laptop trying to send your video stream out to 50 different people, it just sends one single stream to the SFU.
The absolute best analogy for an SFU is a television broadcast tower. A TV studio sends its one signal out to the tower, and then the tower does all the heavy lifting of blasting that signal out to thousands or millions of homes at the exact same time. The SFU does precisely that, but with your video.
So that's the whole magic trick right there. Your computer only has to do the work of sending one single video stream. That's it. And the powerful SFU server handles the massive job of duplicating and sending it out to everyone else. This is how you can be in a meeting with hundreds or even 1,000 people, and your computer doesn't just completely melt.
So as our little data packet finally reaches its destination, let's just zoom out for a second and look at the big picture. What are the key ideas, the core principles of this invisible architecture that makes everything work so seamlessly?
Well, this entire system had its ultimate trial by fire during the pandemic because the architecture was designed this way with these separate components like SFUs that you can just add more of. Zoom was able to rapidly expand onto cloud services like Amazon Web Services and Oracle. This is called horizontal scaling, and it is the single reason they were able to handle that 30x explosion in users.
So if you're an aspiring developer or just curious about how this all works, these are the concepts that truly matter. Things like scaling horizontally instead of vertically, being obsessed with minimizing latency by having a global network, choosing the right tool for the job, like UDP instead of TCP, and using incredibly efficient architectures like the SFU. These are the fundamental building blocks of the modern internet.
And that really brings us to the final thought here. The next time you click that Join Meeting button, you'll actually know about the unbelievable, high-speed, globe-spanning journey your data is about to take in less than the blink of an eye. And it kind of makes you wonder, doesn't it? What other simple things that we use every single day are powered by this kind of incredible hidden engineering?